And we're back. Welcome back and happy Thursday. Today we will continue on, finish up with our coverage of the transport layer and pivot to relatively introductory material on the network layer. But before we begin, some administrative bits. Homework number 3 concerning the transport layer is on the course Blackboard. It will be due a week from today on the 18th, Thursday, of March 2021 at the usual 1 second before the stroke of midnight. Why don't we continue on? When we last left off, we talked about causes for congestion control, and we alluded to the fact that congestion can be caused by another end-to-end path that shares routers along the route of an entirely different communication between two endpoints. And so when a packet is dropped, we said, it becomes particularly damaging or more detrimental the closer that drop occurs on a multi-hop path, the closer it occurs to the destination, because it means that all of that effort was wasted in transmitting it, storing, and forwarding it across the network up to that point. All right. So why don't we continue on to TCP congestion control. Now, in congestion control, we talk about a so-called maximum segment size, or MSS, for TCP, and that represents the total payload area associated with data trafficked between the transport layer endpoints by TCP. And we talk about MSS because the number of bytes that are stored in the payload area is how you measure the rate of data that goes across the network during your round trip time. Okay, so congestion control in TCP modulates or changes the size of the sender window in response to a number of probes testing for the usable bandwidth. And so TCP says, okay, let me send some data at a certain rate, and then let me increase that rate and increase that rate until, the network breaks, namely a loss event occurs. Now, in response to this loss event, the sender window is shrunken, made smaller. If there is no loss event, then TCP says, okay, let me increase it some more. And this increase is so-called additive increase. This congestion window, or CWIND, is increased by 1 MSS, 1 payload's worth of transport layer data for TCP, every round trip time. What does that mean? When you get an ACK, you say, oh, well, there's nothing wrong with the network or the pathway between the sender and receiver, so let me increase my sender window by 1 more MSS. And if there's a loss event, that decrease is so-called multiplicative decrease, meaning that the size of the congestion window on the sender side is cut in half. You want to slow it down, pump your brakes, so to speak. And so this leads to what's called in networking an additive increase, multiplicative decrease that describes the dynamics, i.e. the change in size of the sender window in response to these loss events, whether there's no loss event, i.e. it receives an ACK, or there is a loss event where it cuts it in half, it slows it down. This leads to a sawtooth. This additive increase, multiplicative decrease behavior leads to sawtooth profile for the probing of bandwidth by the sender's TCP runtime. And so here in this graph, we have time going along the horizontal axis, and we have the congestion window size along the vertical axis. And so as we see, you have your additive increase, you get a loss event, the window size is cut in half. Additive increase, loss event, window's cut in half. Sometimes that additive increase, it keeps increasing and increasing. Other times, it gets a loss early. So we increase and loss, continually probing to see just how much traffic the network can handle. So this is the sender window dynamic behavior the size in response to the network loss events by the TCP runtime, the transport layer sender window. So this is a depiction of the sender window in TCP, and here we have congestion wind or C wind, and that is the size of the sender window for pipeline data protocol, reliable data protocol. And so the sender then will limit its transmission based on the sequence number scheme for TCP, which is the offset in a stream of virtual stream of bytes. The last byte sent minus the last byte acknowledged or ACK is going to be the max size of the congestion window. And so this congestion window can grow in size or shrink in size. When it shrinks in size, it's limiting the number of unacknowledged packets that are in flight. If it increases C-wind, it increases the number of unacknowledged packets. And we know now if a pipeline protocol can have a number of packets sent back to back to back that are in flight, that increases the utilization end to end, you get higher throughput, higher data rate. And so this C-wind variable that limits or grows or dictates the size of the sender window responds to loss events associated with congestion. So it's dynamic, and it's a function of the measured or perceived network congestion. Now, if we look at the TCP sending rate, it's sending C-wind many bytes, and it waits for one round trip time in order to receive an ACK, and then it sends more bytes. And so we think about the rate as being the number of bytes, the congestion window, divided by the time, round trip time, and that's the time to get acknowledgement, and that's in bytes per second. Now, let's take a look at how it ramps up the size of this congestion window, this additive increase that we alluded to before. So when a connection begins, it starts to increase that rate exponentially until you get a first loss event. So you start out with 1 MSS worth of data is the size of the congestion window. And you're going to double this congestion window every round trip time. It's done by incrementing the size of the congestion window for every single ACK you receive. And so this incrementing for each ACK means that for each message on subsequent rounds, once you get an ACK, you're going to now double the amount that was sent. And so it has this effect of an exponential increase. Now, of course, this initial rate is slow. It starts out at 1, then goes to 2, then goes to 4, and then it ramps up really fast, really, really quickly. And so here in this network protocol diagram, we have host A on the left, host B on the right. You send one segment, get an ACK, so you increment the congestion window. So now it's 2 MSS's worth of data. So now you send 2 segments back to back. For each one, you get an ACK. You increment the congestion window. So for the first ACK, it now is 2 different segments. So you send those, 1, 2, and then the second ACK, that's 2 more segments, another segment, so that's now 2. So it increases to 4. And so this repeats, and you start out with 1, go to 2. From 2, get those 2 ACKs, go to 4. 4, get the 4 ACKs, go to 8, and so forth. So this increases the send rate very, very quickly. The end effect of this additive increase upon receiving each ACK is to double the effective send rate per round trip time. And so we said that the sender, and more correctly, the congestion window on the sender that dictates the sender window size on the TCP runtime in the transport layer, it responds to different loss events. And these loss events can occur for one of some number of reasons, one of which is the timeout. That's a very hard thing to happen because it means that things went dreadfully wrong. A packet took too long to be delivered because you did not receive an ACK. So in response to that timeout, the congestion window is set back to the beginning again, 1 MSS. And then it repairs that size, probing again from the slowest rate with that additive increase growing exponentially again to some threshold. And then once it hits that threshold, which it remembered, aha, when was the last time that I experienced this hard loss event? It starts to grow linearly. So it reaches that point just before last time it had that timeout event, that loss event. And then once it gets to that point or near that point, it then grows the send rate, the congestion window, linearly instead of this doubling. And so kind of like dipping your toe in the water, trying it out, right? So if you have another type of loss event, a triple duplicate ACK, what happens when you have a triple duplicate ACK? It means that there was some loss event, but you still got these ACKs in return. So that means there's still some available bandwidth in the network. It's not completely broken. And so the response in so-called TCP Reno version or implementation of TCP, it sees a duplicate ACK, and it's indicative that the network, while approaching congestion, starting to teeter on the edge, so to speak, it's capable still of delivering some segments because you got the ACKs. And so what happens is that the congestion window in response to these triple duplicate ACKs, it's cut in half. And it says, okay, well, I had a successive doubling and I got triple duplicate ACKs, so maybe that was too much. Let me cut it back in half, right? You undo this doubling associated with the additive increase, growing of the congestion window size. So once you cut it in half, you then grow linearly, kind of more slowly increasing, not doing this exponential increase, this successive doubling. There is another version of TCP called TCP Tahoe, and it always sets congestion window to 1 if you have a timeout or triple duplicate ACKs. So it takes the same response, says, let me start from scratch again and start that exponential increase using that additive increase approach to growing the congestion window size, 1 increment of MSS per acknowledgement. Okay, so let's take a look at the difference between the sender window behavior for TCP Tahoe and TCP Reno. And so we start out with the vertical axis, that's the transmission round. So these are just time steps, 0, 1, 2, 3, 4, for each round of sends representing a sender window. And on the vertical axis, we have the congestion window, which is measured in terms of number of segments in this graph. And so we have this blue line, that's TCP Tahoe, and this black line is TCP Reno. Again, to jar your memory, TCP Tahoe starts from scratch again, 1 MSS when it gets the loss event. TCP Reno starts from some threshold that it backed off at and gingerly approaches 1 linearly, 1 MSS at a time instead of this exponential increase, this successive doubling. And so here we also have a variable called SS thresh, slow start threshold. And this variable slow start threshold is used to remember what the window size was when we have the loss event. So let's imagine for TCP Tahoe, the slow start threshold was set to 8 segments, and TCP Tahoe started from 1 MSS, went to 2, and then 2 went to 4, and 4 went to 8, and let's say that 8 window size for TCP Tahoe, the sender window, was at the slow start threshold, SS thresh. It then increases linearly. And so we see now in the next round from 8 it goes to 9, then 10, 11, and then 12. And let's imagine we had a hard event, we had a timeout. Now TCP Tahoe will drop all the way back down to the beginning again. The congestion window starts at 1 MSS worth of payload data for round trip time. And so it goes from 1 to 2, that's successive doubling, from 2 to 4. And then once it gets to 6, let's see what happens. We started out at 12, we got a loss event, so it remembers a slow start threshold of half of that. Half of 12 is 6, that's SS thresh. So when it's ramping back up again, exponential increase, once it hits 6, it starts to increase linearly. So it's gingerly approaching the probing of the network instead of the successive doubling, because the last time it doubled, it went to 12 and had that loss event. All right. So let's take a look at TCP Reno. TCP Reno, when we have that loss event, well, we go down to 6, and TCP Reno starts from that SS threshold. Instead of warming up again from 1, it does that linear increase from 6 to 7, 7 to 8, 8 to 9, and so forth. And so the difference between TCP Tahoe and TCP Reno backs off by halving the congestion window, so it cuts in half the send rate per round trip time and increases linearly beyond that, where TCP Tahoe starts from scratch again with 1 MSS and goes into that slow start, that successive doubling until it reaches the threshold and then goes linearly. And so they both go linearly from the threshold. TCP Reno starts directly from the threshold, but TCP Tahoe does that slow start, that successive doubling, the exponential increase up to the threshold, then goes linearly. Okay, so let's look at a finite state machine that describes congestion control for the TCP window behavior, sender window behavior. We start out here in what's called slow start. We have our congestion window set to 1 MSS, our slow start threshold, and our duplicate ACK count. If we get a timeout, we cut the congestion window in half, and then we start from scratch 1 MSS, and we set our ACK count back to 0. If we get a duplicate ACK, we keep incrementing our ACK count. If we get a new ACK, we have that additive increase. The congestion window increases by 1 MSS, and if you do that for each ACK, the end effect is that the congestion window does a successive doubling. So we transmit new segments as allowed. So now, if the congestion window is greater than the slow start threshold, that's where you do the linear increase. And so new ACKs subsequent to that slow start threshold are going to increase the congestion window, but this time a fractional amount of an MSS per round trip per ACK. And this is going to be equal to the end effect of a linear increase of 1 MSS per round trip, because you're only increasing one fractional component, MSS over congestion window. And if you do this enough times for the congestion window, well, you end up getting 1 MSS per round trip time for the entire send window. And so we also set the duplicate ACK to 0 because we got a new ACK. It's not a duplicate. Likewise, if you get a duplicate ACK, you increase the duplicate ACK count, and that's called congestion avoidance. And so it's slowing down, not doing the successive doubling, this additive increase. It's doing a linear increase per round trip time because it wants to approach more slowly the limits of the network because we exceeded it with the successive doubling. So once you get a timeout event, you cut your slow start threshold in half, your congestion window in half, and that's your slow start threshold. And then you set your congestion window to 1 MSS. That's starting from scratch again. Likewise, if you get a triple duplicate ACK, your ACK count reaches 3, then you cut your congestion window in half, and that's your new slow start threshold. And then you increase your congestion window by slow start plus 3. Why plus 3? Because that's 3 duplicate ACKs. You had 3 inbound pieces of data that came into you. And then you have something called fast recovery. Fast recovery is when you're warming up again. If you get a duplicate ACK, you increase the congestion window by 1 MSS because you're getting new data. Likewise, if you get a new ACK, your congestion window is set to the slow start threshold. Your duplicate ACK count gets reset. And so we have these 3 operating regimes. You have the slow start. That's the increasing exponentially of the congestion window to try to get to the point where the network, just before the network broke or had a loss event. And then you start to go linearly. You're avoiding congestion. You're slowing down your rate, increasing linearly instead of the successive doubling. And then you do the fast recovery. If you get that hard event, that loss event, you know things are starting to fall apart. You cut your window size, and then you start increasing again. And so if you have a timeout, that's the worst thing that can happen. That means the network is congested. You cut your congestion window in half, and you put C wind, your SS threshold rather, is the congestion window cut in half. So you're remembering that point just before your successive doubling broke the network, i.e. caused congestion. You set your congestion window to 1 to start from scratch again, sending 1 MSS per round trip time. And then you transition back to the slow start to start that multiplicative increase by adding a new MSS per round trip time each time you get an ACK. And so we have slow start, congestion avoidance, and this fast recovery all together transitioning in concert to grow the size or shrink the size of the congestion window, the sender window size, thus slowing down or speeding up the send rate. Now, of course, with that fast recovery, you are starting from scratch again, 1 MSS, and then doing the slow start. And so it recovers eventually. All right, and the timeouts drive all of these events and the new ACKs as well. And so if we look at the throughput, we said that the congestion window with this additive increase and this cutting in half of the congestion window, the sender window size, that results in a sawtooth behavior for the size of the sender window. And so we go from window size over 2 to window size, loss, window over 2, loss, over 2, increased, loss. And over time, the average is right in the middle, which is 3/4 of the window size divided by the round trip in bytes per second. All right, so the goal of TCP is the statistical sharing, and it has a fairness goal in order to share equally in the bandwidth of a shared link. And so if you have two connections via TCP and you have some bandwidth R, each should get a fractional rate of R over 2. If you have an arbitrary K many TCP connections, each one gets an equal share R over K. And given this sawtooth behavior, the additive increase, multiplicative decrease, and the fast recovery, it converges onto fair sharing should these connections remain open, sending data at the same time, which is kind of neat, right? You get this sharing. And so here in this graph, it's a depiction of the sender window behavior and how that converges over time onto fair sharing of the available bandwidth on a link. And so along the horizontal axis, we have the first connection with a throughput R, and the second connection is on a link that has that common bandwidth of R. So we have two connections over the same link with a total bandwidth of R. And so here, this dotted line, 45-degree line, represents the equal bandwidth share. And this blue line represents the bounds on what that bandwidth share can be. If we go for connection 1, using up all R bits per second, that means there's no bandwidth for connection 2. Likewise, if we use up all the R bits per second for that link, that bandwidth, with connection 2, that means there's 0 bandwidth for connection 1. And this dotted line represents the equal share, and this dotted line goes up, goes up, goes up until we hit R over 2. So if we project that down, that's R over 2. If we project that equal bandwidth share to the left, that's R over 2. And so this R over 2 represents the equal bandwidth share between the two connections. And so let's say we have these two connections and we're doing the additive increase. So we start going up, 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 this additive increase for the two links, and it doesn't matter where you start, we're just starting here. And so it goes up 1 MSS per ACK as you get these acknowledgments. We're doing that for connection 2 and for connection 1. So we get this line going up at this 45-degree angle from the starting point. Then all of a sudden, we get a loss event. So what happens? The congestion window size is decreased by a factor of 2. So we decrease by a factor of 2 in that direction, and we also decrease by a factor of 2 in this direction. And so we get this new point. Now all of a sudden, we go back to additive increase. So that's 1 MSS per round trip time for each ACK that comes back. So we go up at 45-degree angle again. So all of a sudden, we get another loss event. So we cut in half in this direction to the left, and we cut in half along going down in the Y direction. And so we end up with this bandwidth for the window associated with connection 1 and connection 2 TCP sender window. And so we increase again, and then we get the loss event and increase again, and each time it goes back and forth and up and back and up and back, and it eventually converges onto this equal bandwidth share line. So it doesn't matter what the initial send window size is for each of those connections, eventually it converges onto the equal bandwidth line, and they're fair sharing the available bandwidth R bits per second for that shared link. And we converge. So TCP is fair, and that can be a good thing. It can also be a bad thing. Now, with UDP, multimedia apps typically do not use TCP. They don't want the send rate throttled by this congestion control. They want to use up as much bandwidth as possible. And so UDP is a good choice for multimedia because it needs that high send rate. And so when you use UDP, you're sending audio and video at a constant rate, and those applications can tolerate packet loss anyways. So you don't want that fair sharing afforded by congestion control. Now, if you have parallel TCP connections, certainly an application can open more than one TCP connection between the same host. So you have a process on host A, a process on host B, you open up a bunch of connections. Each TCP connection, not an application, but connection, is getting an equal share of bandwidth. And so web browsers do this. Suppose you have a link at rate R, and you have 9 existing connections. Let's say a new application comes along and it asks for 1 TCP connection. It's going to converge through the additive increase, multiplicative decrease to an equal share rate. So that was the original 9 connections plus that 1. Each app is going to now get 1/10 of the available bandwidth. But if that new application, given 9 existing applications, decides to open 11 TCP connections, well, that particular application is now going to get 1/2 of the available bandwidth. And so TCP is fair per connection. And so you could suck up more than your fair share of bandwidth by just opening multiple connections and using them for your purposes between the client and the server. This congestion control, we said, works by probing. And we have the sender modifying its send rate, namely its congestion window size, sender window size, based on the perceived loss events, whether that's a timeout, an ACK, which connotes no loss, or a triple duplicate ACK, which means that the network is starting to get a little bit shaky, teetering on the edge of congestion. And so there are explicit methods for congestion notification, so-called network-assisted congestion control. And with this, the philosophy or the thought is who better to inform the communicating endpoint, namely the sender, about congestion, who better to inform than the router itself. And so in the IP header, in the network layer, there's a field, TOS, terms of service field, and it's marked by the router to indicate congestion. And so this datagram comes across the router. The router sees that it's getting congested, its buffers are near to full or already full, and then it marks this packet that goes across the router anyways, saying that, yep, I'm congested. And so what happens then is the source of the message, the datagram from the network layer, sends its datagram across, and it's marked by the router. So when it gets to the destination endpoint sees that this explicit congestion notification flag is set, and it says, okay, when I send the ACK, I'm going to notify the sender by setting an ECN, explicit congestion control notification bit, and it set that flag, and that's payload on the ACK. So we have our source, and here's our datagram. It sends it across the network. It's marked to note that there's congestion if the router sees that its buffers are near to full. It gets to the destination, and when the destination returns an ACK back, it sets the explicit congestion notification bit, and the source gets it and says, there's congestion in the router. Let me adjust my window accordingly. All right. So with that, we have completed our study of the transport layer, and next we will continue on one more layer down to the network layer and talk about its structure. So we're here in the network layer, and we're going to get this started and talk about the network layer. We won't go through all of the material. We'll save that for a subsequent module. And so we'll start out with an overview of the network layer. The dichotomy in which modern network layer is discussed is the so-called data plane and the control plane. Now, the goals of our treatment with the network layer, yes, we'll go into more detail, but want to understand the principles behind the services afforded by the network layer. Now, in the beginning, we'll focus on the data plane, and we'll look at the service models, we'll look at the behavior, we'll look at how a router works, how forwarding is implemented, and generalized forwarding overall. And we'll look at the instantiation and implementation of the modern internet. And so the network layer, what does it do? Now, we talked about segments in the transport layer, and these segments are passed into the network layer beneath the transport layer. And the network layer's job is to identify the host, more correctly the network card, which is the destination of this particular segment. And that segment is stuffed as payload into the payload area of the network layer packet, and at the network layer, we call it a datagram. And so that datagram has inside of it a payload area that has the entire segment replete with one MSS and the transport layer headers. And so this network layer datagram then adds its own header information that allows it to identify the network card of the destination endpoint. On the receiving side, once this datagram comes in, it unwraps the segment from out of this datagram and then sends it to the transport layer above. And so the network layer protocol exists on every single host, whereas the transport and application layer only exists at the edge, namely the end systems on the network. And so we have these network layers that are on the routers in addition to the host or the end system. Now, the router examines the network layer header fields in all the datagrams that pass through it and make a determination that we'll talk about in a moment based on that header information. And so here we have our end systems, our hosts at the network edge. We have a client machine, a laptop up above, and we also have a server at the other end of the network down below. Now you notice here they have all 5 layers: physical, data link, network, transport layer, and application layer. And so when you originate a message, also the routers have what are called layer 3, the so-called layer 3 devices, because the routers also have a network layer. They also have a physical layer, data link, network, and you notice here the routers don't have a transport or application layer. That complexity is deliberately kept at the edge of the network because simple things can be made very, very fast. And so we have all these layer 3 devices, namely our route infrastructure, and then we have these 5-layer devices, namely the end system. And so when you originate a message, it's encapsulated with header information, and the routers examine this header information in the datagram, forwarding it to the output link that it should go to until it eventually makes its way to the destination endpoint, and the network layer on the destination endpoint delivers it to the transport layer, which then sends it to the correct socket using the destination port, and you get that on the other application at the other end of this communication. And so let's look at the network layer functions. There are 2 basic functions for the network layer. One is called forwarding, and that's the switching decision, moving packets from the input port of a router to the output port of a router. And then there's the so-called routing decision. Now, the routing decision is a global decision. You're taking in information about all the routers on the network and determining the pathway that datagram should take. And so forwarding is a local per router decision, but routing is a global across the routers decision. And so the analogy that they use in the book, and the book is quite good about this, forwarding is the process of getting through a single interchange, say on a highway, but the routing is the process of planning a trip. You take a left at this intersection, you go down that road, you get to that juncture or intersection, then you go to this other road. It's the overall global decision. And so the router, we separate our network layer into the so-called data plane and the control plane. Now, this is the modern treatment because of something called software-defined networking. Now, the data plane involves the local decision per router, and it determines how a datagram that arrives on its input should be forwarded to some output. And so here in the diagram, the so-called forwarding function, we examine the bit information associated with header in the router's fields, router headers, and it comes in on some input port, and you'll notice here the output ports or output links on the router are labeled 1, 2, and 3. And so based on what the pattern is of the bits in the network layer header, that datagram's header, it's going to make a decision, okay, this packet should go out that particular link. And so the control plane is that global decision that uses network-wide information to determine how a datagram should be pushed out of the various links in order to make its way from one destination to another source, to another destination, from one source to another destination. And so here we have 2 control plane approaches. One is the traditional approach, so-called traditional routing algorithms, and here we have processes that run on the routers and they exchange information with one another, and based on that information they exchange, come up with a path or determination. There's also so-called software-defined networking. Instead of having routing algorithms running on each router exchanging data, we have routing agents running on each router, and they collect this data, send them to a centralized server. It could be a cluster. It determines what the route is and pushes that result back to the routing agents. And so here we have a diagram. We have our routers down below, and inside of each router, we have something called the local forwarding table. Now, this local forwarding table has entries associated with patterns of bits for network addresses, and based on what these patterns are, what range these values are in, it has an associated output port for each pattern. And so this local forwarding table implements the switching decision that says if I see a datagram with a certain type of address, is it going to go out port 3 or port 2 or port 1? And so the routing algorithm also runs on the router. It's nothing more than a specialized computer with multiple network interfaces. And this routing algorithm talks to other routing algorithms for routers that share a link with it. And so they're exchanging all sorts of information about the traffic conditions on all of these links. Now, based on these traffic conditions that are collected in aggregate from all of its neighbors, these routing algorithms determine the path and then download a new version of the forwarding table to be installed into the router to implement a new switching or forwarding decision. And so the switching or forwarding decision is implemented in the data plane that consists of the forwarding tables that control the forwarding behavior of these routers, and the determination of which set of forwarding table entries there should be, implementing the paths that the datagram should take through this routing infrastructure. That determination of the routing algorithm, the collection of the data, determination of the route, that's called the control plane. It controls globally across your network where these flows of datagrams should be going. So if we look at the software-defined networking version of the control versus the data plane, instead of these routing algorithms, we have what are called control agents. And these control agents live on each of the routers, and these control agents participate in sending and receiving information from a cluster or a machine called a controller. Now, these control agents, they send local traffic information from the router up to the controller, which is centralized machine or cluster. Now, this cluster then computes the routes, determines the global path information that datagrams should take based on their destination addresses, and it sends them down into the control agents that install them into the router to change or update the local forwarding decision. And so in this, we have the data plane, and the data plane, again, consists of the installation of these local forwarding tables by the control agents, and the control plane in software-defined networking is a little bit different. It's this remote controller. Now, the interesting thing about this is with an API called OpenFlow, you can now, as part of your application, your network application, establish what flows or pathways are most amenable to the particular application. And so a lot of the functionality in this controller for path determination is made available through some software service-oriented architecture type of call. All right, so one of the questions that one would ask is what sort of service model do you have for the channel to transport these datagrams from the sender to the receiver? And so you might want guaranteed delivery, or you might want certain types of flows to happen, or guaranteed bandwidth. And so let's take a look at what is inside of a router. Now, a router has many aspects of what used to be parallel computing. And so here you have an input port for the router, so that's the incoming traffic, and then you have an output port. Now, connecting the input ports for the output to the output ports is a high-speed switching fabric. And then you also have a processor, so-called routing processor, and this is this chip running processes like you'd have in a typical host or machine, and it's going to run algorithms, or it's going to run these control agents. And so if we take a look at this dichotomy of the control plane versus the forwarding plane consists of the input and output ports and this switching fabric. Now, when you install a forwarding table, the switching fabric is established to get certain inputs to certain outputs, certain packets that arrive on the inputs to get them to certain output ports. Now, the control plane deals with the routing and the management, and this operates at a much slower time scale than the forwarding plane. The forwarding plane is typically implemented in hardware, and it's very highly specialized hardware, and it operates in nanoseconds time frames. It's very, very fast. But the control plane operates in milliseconds. It's computing things. It's arbitrary computation to establish these routes and also exchange data. And so let's take a look at the input port functions. Now, we start out with 3 stages, and these stages consist of line termination that deals with the physical layer, namely the signal energy that encodes the bit level data. And then we have a stage for the link layer. That's the sending and receiving of Ethernet frames, units of data. We'll talk about link layer in Chapter 5, but it's the sending and receiving of bits for routers or devices that share the same network, the same physical connection, be that wired or wireless. And then we also have the lookup and forwarding portion. It was where a queue is implemented, and this queue is going to store incoming datagrams should the forwarding across the switching fabric not be able to keep up with the number of datagrams that are arriving or incoming. And so we have a decentralized switching system here. This stage acts like a parallel processor in a parallel computer. And so using the field values for the datagram, the header values, it looks up an output port and it uses the forwarding table in order to send across the switching fabric this datagram to the correct output port. And so it looks it up using something called a match plus action. For any particular match, it takes a certain action. And the goal is to complete this processing, this forwarding of datagrams across the switching fabric at so-called line speed, at the same speed in which they come in. Now, of course, if it can't keep up, it's going to queue those incoming packets. They're going to wait in line inside a queue, so there's also buffer space. And router memory is very, very expensive. And when you buy an enterprise router, oftentimes what you're paying for is the amount of specialized memory as well as how fancy the switching fabric is. And so this is decentralized switching. And you have also destination-based forwarding. You forward based only on the destination of the destination IP address. This is indifferent to using the software-defined network approach. It's very different. You can also have what's called generalized forwarding. We can set a series of rules that will make the router take certain actions based on how various pieces of information in the datagram are matched to those rules. So this is a basic forwarding table, and here we have 4 entries, and we have an address. It's a dotted quad, and that's the form of an IP address. Now we take each one of these 8-bit numbers, and we write out their binary representation and separate them by periods, and it looks like the following. So we have 200.23.16.0, that's this first address, through 200.23.23.255. Now, of course, any address whose range of addresses is within this range is going to be looked up. When it matches this rule, it's going to say, all right, well, I'm going to send this particular datagram out of link interface 0. Likewise, if we get these other matches, it's going to send out of link interface 1, interface 2, and you can also have default rules, interface 3. And so the interesting part is these correspond to blocks of addresses. And these addresses are unique, these IP addresses. They're associated with unique network cards. And so here we have one range or block of addresses. And you notice here we have all zeros for the least significant bits. And then here we have all ones. So imagine all those addresses that you have between all zeros and all ones for those first several bits, incrementing by one at a time. Each one of them is a separate address. And so therefore, we have an entire block of addresses or range of addresses that's represented by each one of these matching rules in the local forwarding table. But one of the key considerations is what happens if you don't divide them up into contiguous blocks or ranges of addresses. Well, that's also been handled. The matching is based on the so-called longest prefix. Because one of the things that can happen is you can take some subset of addresses within a range and physically move them to another network. And so if you do that, you have to make sure that your datagrams can find the right destination should that network the address change its location to an entirely different network. And so using longest prefix to match addresses to port numbers for forwarding is how that's accomplished. And so here we have a bunch of destination addresses, and we have one address that's defined up to this bit, and then we have another that is defined 3 more bits, and then we have another that is 0011 in the third dotted quad, and then it's all wildcards after that. So what's going to happen then, if you have some addresses, the first choice that it makes is to match to that rule that has the longest prefix or the longest defined set of bits for that particular address. And so here, if you had this first destination address, it's going to match, let's see, we have 1 0 and then 1 1. So we have 1 0 in this field, and that's going to match exactly this one. If we have 1 1, okay, well, it could either match this one or this one, but then we see we have 0 0 0. That's the longest prefix over here, 0 0 0. So it's going to match this rule. And so go out interface in the first case, this is going to go out interface 0, and the second one is going to go out interface 1. And so with this longest prefix matching scheme, we can disambiguate if we have 2 rules that appear at face value to match a destination address. So we always resolve it to a single destination address. There's never ambiguity. All right. So with this longest prefix matching, we'll actually demonstrate a little bit later in this module on the network layer, specifically why this longest prefix matching is important. And we'll actually have an example where we move an IP address to a different service provider to show that it can still match because of this longest prefix matching scheme. And so when the router is implemented, it actually implements in hardware content addressable memories the ability it implements to look up these patterns of bits representing blocks or ranges of addresses. The only way to get this stuff to scale is to do it in hardware, and that's exactly what it's done. So with that, we will end there, and we will pick back up on Tuesday. As usual, please stay healthy, stay safe, and I'll see you all on Tuesday.